Okay, hi everyone. Welcome back to the week 12 doubt clearing session for aluminum based alloys and metal matrix composites. I'm Ananya Nag. I'm a PhD student at IIT Delhi, and this is the last week of this session of MM40. So, whatever doubt you have till 12, week 12, you can ask. Otherwise, we'll start with the topics of week 12. If you have any doubt till week 11, you can ask. We were having,
Uh,
yes,
yeah, good evening, ma'am.
yes.
Ma'am, actually, I had one doubt. Uh, Basically, there is very small doubt regarding tensile strength and hardness.
Okay.
So, uh, I want to ask, ma'am. In my research area, I have gone through some of the papers, and mostly most cited papers I have gone through, and after reinforcement of the nanoparticles, take example taking SiC or TiC. So there is not much changes in tensile strength, but there is change in hardness because I have seen most of the paper. So like tensile strength is not changing after reinforcement, and if it is changing, means it is changing very minutely. Uh, but hardness is changing. Like hardness is more than 100%, but tensile strength is always reduced after reinforcement, or it may be same, or I think it is not same, it will always be reduced. So can you explain the reason of it?
Okay.
Means
So I'll ask you one question that what is tensile strength and what is hardness? What do you mean by tensile strength and hardness? In
ma'am,
simple language, you tell me.
okay, ma'am. Ma'am, actually, tensile strength, what I understand is percentage elongation,
Yes, okay.
right?
So that is tensile strength, stress or
Tensile
strain.
stress, tensile stress means if we are applying load, like in any axial load, so
Yes.
how much load the material can bear without failure? Means we can say without plastic deformation.
Yes. So without being plastically deformed, up to that limit, how much stress I can apply, that is known by tensile strength. But what is hardness?
Uh,
Hardness means that when you are trying to deform the material, how the material is deformed means what is the effect on its surface. Are you trying to say something, Vanshika? Okay. So if there is a material, okay. If there is a material, so if I am giving one tensile load, then it will deform, and if the load is up to this limit or this limit, the shape and size can be regained. That is tensile strength. But hardness means if I am indenting over this using nano indentation or other methods, how the surface is getting deformed. If the surface is not getting deformed, means it is having very high hardness. Now you think about the metal matrix composite, where you in aluminium you are adding the silicon carbide or the nanoparticles of uh, titanium carbide, TIC or SiC. Those particles are very hardened particle. Those particles are brittle particle. So whenever you go for the hardness measurement, obviously the hardness of the metal matrix composite will always increase because of those mixing of those particles. But if I talk about the tensile strength, then again, if the matrix is brittle or the matrix is ductile, then on the tensile load application, the things will act like that. Whether there will be particle fracture or there will be deformation in the matrix only, those things, or how the elongation is taking place. So if you notice, if we go for any type of testing, low cycle fatigue or high cycle fatigue, we'll go up to certain point to which we can always regain our original shape and size of the object. But if you are dealing with metal matrix composite, that elastic region is not been talked about much in the week 12 lectures. We were only talking about the plastic region, because obviously there is some embedded particles over the matrix, and if you are applying some external load, there can be detachment with the particles in the matrix, or the particles can get broken down due to that load, because the matrix is ductile, it can regain its shape and size, but the particles are brittle. So those type of scenarios can take place. This is why the tensile strength we cannot comment on. It will reduce, it can be same, it can increase as well. Maybe the percentage of increasing tensile strength is very less, but the hardness will always increase.
Okay, ma'am. Ma'am, if take example, if we have a precipitation hardening in case of six results like Mg2Si formation is there. So in this case, can we say like because of the precipitation hardening, the strength of the material increases,
Yes, so
right?
that is
So
alloy.
that strength is what? It gives hardness or it gives like tensile strength.
Okay, one thing is, first of all, strength is increasing means not tensile strength, that is the hardness. Because there the strength is increasing means, if now you are applying some load, it can restrict. Yeah, you can say tensile strength, because it will restrict that elongation part, because there is some precipitate. But again, those precipitates or second phase particles are pre-alloyed, means alloyed to the matrix. So there the scenario is different. Whatever way the aluminum will act under the load, the same way the precipitates will also act. Maybe there will be some difference in between the effect of or acting of the aluminum matrix and the precipitate, but it will be almost equal. But in case of metal matrix composite, both the elements are having a very large difference in their properties. So this is why here the tensile strength will not increase.
Okay, okay, ma'am. Now I understood. Because actually Mg2Si is forming because of the element present already in it. But here we are adding some particle from outside, so it may like tensile strength will not increase, but hardness will increase because of the formation of, because of we cannot have a grown means a grain growth here because the particle is
See, the
sitting between these
hardness
two grains
means
and
in
all.
case of alloy, when you are going for alloying, the hardness will be connected to the strength as well. So when you are increasing the strength of the alloy, the hardness will also increase, because you are actually hardening the material. But in case of metal matrix composite, the strength may increase, the strength may not increase, but the hardness will increase. And strength means I'm talking about the tensile strength, because there the particles are embedded in the matrix. If there is a lot of difference in the metallurgical property between the particle and the matrix, you cannot comment on the tensile strength in that case. But you can surely say that yes, I am 100% sure that the hardness will increase. Like in
Ma'am,
alloy, I am
ma'am,
saying that I am 100% sure that if I am doing some precipitation hardening, the strength will increase.
Ma'am, I think that is a reason like proportionality limit is decreasing in this case.
For
Like
which? Okay, yeah. So
in metal
tensile
matrix
strength is
composite.
that na ki up to which point you can restrict the tensile, means elongation, percentage elongation of a particular object.
Okay, means ma'am, the data which we are getting in tensile strength is like up to elastic limit. Means the point from where the elongation start up to that point, how much load the material can bear. That is tensile strength, right?
Not
Because
elongation, but plastically deformation starts.
plastic deformations.
Hmm.
Okay,
Because
okay,
in
ma'am.
the whole,
Now I understood. Yeah,
okay, okay, because the
yeah.
in the whole proportionate limit, in the whole Hooke's law region, there will be deformation, but the
Mm.
deformation will be regained as soon as you unload the material.
Mm-hmm. Yes, ma'am. Actually, that's what I confused because in all the reinforcement of the particle, they were not discussing about the tensile strength. They're only discussing about the hardness. If we are increasing the percentage, means volume fraction of the particle, like from 5 to 13%, the hardness will increase, but no much changes in tensile strength. But we are discussing like in alloys, there is a tensile strength as well as
Actually, the
hardness, both are
tensile
increasing.
strength will decrease. Why?
Yeah.
Because if there is a alloy, if this is alloy, suppose, so you are stretching the thing, this will stretch because all the grains which are present inside it, it will stretch because all the grains are having aluminum in it. Maybe some portion of silicon and magnesium as well, but most of the things are aluminum. But in case of metal matrix composite, there we are not talking about the grains because they are embedded particles. Now imagine microscopically when you enlarge the when you are trying to enlarge the dimension, this particle may get elongated, whatever we can think of, but these particles are brittle, so it will not take place because these are brittle particles. So brittle particles can get broken down. So this will be the case, but again they are embedded in the matrix, so there will be stress generated around the particle matrix interface. So there was this is why the stress intensity factor was discussed. Due to the stress intensity factor in the interface, there will be changes in the matrix taking place, and this is why the tensile strength will decrease, but the hardness will increase because this particle are very hardened. Hardness is very high of this particle. So overall, the hardness will increase.
If there is a chances of formation of any like intermetallic compound because of the dynamic recrystallization during this process, right? So can we say like because of this intermetallic compound, the tensile strength may increase somewhat, like
If
if we
the
have,
nanoparticles, if the
ma'am,
what
take
say?
example, take example
Yeah, I
like
understand. I
6061.
understand your question. So,
Yes, ma'am.
what I'll suggest is if the particles which have been mixed are nanoparticles, then this phenomena may happen according to the amount of particle that has been added. Because if the particles are more in shape or size, na, there will be a lot of restriction in the percentage elongation. This matrix will feel restriction in percentage elongation. But if the particles are nanoparticle in nano dimension, then the stress intensity factor around them will also be reduced. So if there is some intermetallic formation, there can be one situation like for nanoparticle mixing, there is one decrease in the because because of the formation of metal matrix composite, for whatever it is, nano or micro, there will be some decrease in the tensile strength, maybe this much amount decrease. And again, due to the dynamic recrystallization, if there is some second phase or atmosphere formation or intermetallic formation, and due to which if the strength is increasing, then it may happen that the resultant can be this much, or the resultant can be zero as well, but I don't think that much strength will increase.
Yes, ma'am. The strength will not increase much, but it
There
may
can be
increase
some.
because of this formation.
Hmm.
Right. And ma'am, actually, if you are telling about the size of the particle, so size of the particle is more means we have the more means more like interface, right?
Yes.
With the
No, no,
means
no, no.
because
Less number of interfaces are less, but the area you cannot comment because of how many particles you are adding. Depending upon that, the interface area will be decided.
so like you are telling more elongation and less elongation in case of a small particle. So less elongation in case of a small particle because of what means
Okay, no, 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 not. I'm not saying so. Actually, if the matrix is having the particles in micron dimension,
yes.
then if you are going for the elongation, then this will feel a lot of stress intensity, due to which the
Mm,
del K will be very high, the stress intensity factor, and it
yeah.
cannot get elongated, cannot get
Mm,
elongated, because these are brittle
mhm,
particle. Okay, so what will be the case? There can be breakage in the particles, or the matrix can simply get failed. But if you are mixing the particles which are in nano shape
mm,
or nano dimension, then what will be the case? The area, if this is the nano particle, the area which is having the interface is lesser in this case. So the
mm.
stress intensity factor arising in this area will be less. Del K is lesser than this case. So it can get elongated.
But ma'am, the means the interface is more in case of a small size particle.
Yes, but that depends upon how many particles you are adding. So it's like for metal matrix composites, na? Like for alloys, I can take example of alloys. So what is aging? That when you achieve up to certain dimension of the precipitates, then we'll say that it is hardened. But do we go after or beyond this point? No. This is overaging. What happens in case of overaging? The precipitate size increases, and due to which the hardness doesn't increase, rather the ductility increase, means the hardness decreases. है ना, because there will be lot of space again to for the dislocation to move through the part precipitates. So this happens in case of overaging, na. So there we have a one parameter, we have only one parameter, that is the size of the precipitate, because the alloy that we are using there is having certain amount of aluminium, certain amount of silicon, and certain amount of magnesium, and we are not externally adding any silicon and magnesium in the matrix. So whatever can be the amount of precipitates Mg2Si, the amount is fixed, but the size of the Mg2Si is not fixed. Up to certain size, it will harden the material. Above or beyond that particular critical size, it will be overaging. So it will decrease the hardness. But here, in case of metal matrix composite, you are dealing with two type of things. One is alloy, another one is metal matrix composite. Means the particle reinforcement. If you talk about MMCs, if you forget about the alloy, you just imagine that there is only aluminium. This is aluminium only, and these are the silicon carbide. Then there are two factors. One is the amount of silicon carbide that you are adding. The next is the particle size of the silicon carbide that you are adding. So there was only one what say unknown if there is one equation, there is only one unknown x, that is the size of the mg2si. But here there are two unknown variable. One is the particle size, another one is the particle amount. So you are getting mixed up with these two things. You first take constant one variable. If my amount is fixed, then if I reduce the particle size, means again there will be volume fraction added. But I'm talking about like, if I am adding 5 silicon carbide particles, suppose silicon carbide 5 particles, if these 5 particles are in micron size, then the hardness will increase but the strength will decrease. But if these 5 particles are having dimension like 50 nanometer, then it will increase the ductility rather. You understand what I'm trying to say?
Yeah, ma'am, understood. Because we are increasing the density of the particle.
Uh,
Can we say like
yeah,
more,
so you can say
more and more particle, more and more particle we are adding means like very very small particles.
even if you are fixing up the number of particles that you are mixing, you're
Ma'am,
reducing the size.
because ma'am, my area is fixed. Because my volume is fixed. So if we are see, if my volume is fixed, ma'am, so means if we are adding bigger particle, so it will be less in number. If we are adding a smaller particle, it will be more in number.
No, that's not what I'm trying to say. If your volume is not fixed, if your number of particles are fixed, suppose, because density and volume, these are different things. So you take, if the volume is less, in one case volume is less, in another case volume is high. Now you tell me, uh, if the volume is less means the particles are nano, छोटा छोटा particle है. If the volume of the particle is more, means these are bigger particle. So the interface is more in this case. The interface is less in this case. So the ductility will increase in this case. In this case, the ductility will reduce in this case. Means the tensile strength will reduce, but the hardness will increase. So if I am mixing nanoparticle, then tensile strength will increase because the ductility will increase. The hardness may also get increased. But if you are adding micro or millimeter particles, then the tensile strength will obviously decrease, and I'm 100% sure that the hardness will increase. Now you understand what I'm trying to say?
Yes, ma'am. Ma'am, can you repeat the last point? Like when we are reducing the size, when we are reducing the size, so that ductility will increase. Means reducing the volume of the particle. Why ductility will increase?
Because uh, what is meant by ductility means, when I am doing the elongation in a material, the dislocations are moving inside the material. Okay, so that brings out the ductility in any type of material. But when you add the when you add the particle reinforcement in a matrix, so the particle is uh, holding the matrix. Okay, if this is the particle, suppose it has its forearm and it is holding the matrix. Okay, and now you are elongating the matrix, but it will not uh, lose its hands. So these four are hands of this particle. So it will try to restrict that elongation. So as much as bigger the particle is, the restriction will be more. So the ductility will reduce.
Okay, okay, ma'am.
Okay. But if the particle is lesser in size, so it will have only two hands. It cannot have four arms because it has less surface area in this case. So it will restrict the tensile or the elongation, but it cannot restrict that much. So the ductility will not decrease, it may increase, or it will be equal, same, no effect.
But ma'am, I have one doubt here. If particle size is more, means can we say we have a chances for the grain growth because the very less particle are there in the
Okay.
matrix.
So if there are very less number of particles, now there is one thing. If you always fix the number of particles, okay, by the volume and density and mass calculation. So when you are mixing 10 particles, 10 bigger particles, uh, what was your question? I forgot.
Ma'am, if we have a bigger particle, means
Huh.
there is a chances of grain growth. But
Okay.
because
So, yeah, if there are bigger particles and if you are going for some heat treatment, one can be the situation like if the particles are having a low dysregistry facet, then the particle will provide a nucleation site for the matrix. So there the nucleation may take place. There can be new grain formation, and if you are doing going for some aging, there will be grain growth. So that can be one situation. Another situation is grain growth will not take place if there is a lot of mismatch with the particle lattice and the aluminum lattice or the matrix lattice. So now you ask me your question.
yeah, so ma'am, if number of particle is more means they will provide the pinning effect,
Huh.
right? So if they will provide pinning effect means between the two grain the particle will sit and the grain growth will never takes place means there will be a means we can say the grain growth will be pinned down because of
Yes.
the particle,
So
right?
this one
So
thing was said now, like the particles will have pinning effect in the grain boundaries because
yes,
these are sitting somewhere and there will be pinning effect. So
yes,
yeah, there will be grain growth restriction,
yeah.
but it will be possible when you are going for some casting
Means,
process or so or aging
means
process.
there will not be a coalescence of two grains because there is a particle which is sitting between the grains,
Yes.
so
Yes.
it will pin down
So
their growth.
if the number of particles are more or the particles are bigger, the effect will be more. So there will be no coalescence. The grain rotation will not that much be possible. Those things will take place. So that
Uh,
will be helpful for us again because when we are adding more particles or bigger particles means we are trying to increase the hardness. If we have increasing if we are increasing the hardness by mixing particles, so obviously we want the not to happen the grain growth because grain
ma'am,
growth means ductility will increase.
yes, ma'am. Ma'am, I am discussing about only tensile strength. So if particle size is more, we are telling tensile strength will reduce, right? So tensile strength reduction is because of the ductility, because ductility is getting reduced, percentage
Yes.
elongation is getting reduced. Okay.
Yes.
So if we are adding a more particle, so if we are adding more particle means what will happen is in this case the uh, ductility will also decrease na, in this case also because if the particle is more means if we have a small particles and more particles we are adding, like if we have a particle of 23 nanometer and we are adding, and if these particles are more like 100 particles we are adding
Yes.
in the size of 23 nanometer, and again we are adding the 5 particle of bigger size,
Yes.
right? So if we are adding 5 particle in bigger size and if we are adding means volume is same, I am not like the volume of the particle, the volume of these 5 particle is same as the volume of all these small particles,
Hmm.
right? So I am just I am making the volume constant, just I am reducing the size of the particle.
Hmm.
So if lesser in size of the particle, lesser will be the ductility or higher will be the ductility.
Higher will be the ductility.
Okay, and
because
means
because again when a bigger particle is sitting over there na, the grain boundaries we are getting pinned down. You just assume there is only one particle, this one, okay. Now, if it is sitting over here, the grain which are present over here, the grain boundaries, number of grain boundaries which are getting pinned down because of this embedded particle will be more. So the number of grain boundaries pinned down will be more in this case. But here, if I am considering only one particle, the number of grain boundaries we are getting, which are getting pinned down, is high or low? You tell me.
Ma'am, if the particle is bigger, so if we are taking the bigger particle means the smaller particle will have more number of grain boundary as compared to bigger particle.
No, 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 no. Here you answer me this question. If this particle is smaller, this is the particle. So the number of grain boundaries pinned down by this smaller particle will be more than this one or less than this one?
Will be more than this one, ma'am.
Will be less than this one. Na? This particle is smaller, so it is attached with less number of grains.
Okay.
Hmm. है ना?
Mm.
So
But
there are two things. See, if you are comparing with number of particles means volume of particles, then also there can be difference, but you just try to understand that if this particle, if it has pinned down 10 grains, then it will pin down maybe 3 grains. So the overall resultant will be lesser in this case of smaller particle. But at the same time, the volume is more. The volume is same, so the number of particles are more in case of nano. So you can say the resultant will be same.
okay, ma'am. And
So
we
this
are
is
adding
why the
like
one thing. So this is why you cannot comment on this directly that yes, if you are decreasing the particle size, the ductility will increase. No, if you are going for nanoparticles, the ductility will increase, but it depends upon the amount of particle that you are adding.
okay. And if we are telling about the volume fraction of the particle, like 20% volume fraction of the particle we are adding. So this volume fraction is, let's take in my case, this is the volume of the weld zone, means the 20% volume of the weld zone, or what we are taking.
No, no. Okay.
This volume
In
fraction
weld
of
zone, you are
20% volume fraction or
yes.
13% volume
So
fraction.
in the weld zone, you are adding the powder of the metal matrix composite, right?
Yes, ma'am.
So in the weld zone, whatever amount of aluminum you are adding, you add 20% of the silicon carbide.
Okay. Means aluminium
If you
is
are
the total one.
adding, yes, if you are adding 100 grams aluminum, you add 20, means if you are adding 80-gram aluminum, you add 20 gram silicon carbide. So you mix this 80 gram and 20 gram, and then you add that in the uh, um, that matrix.
Ma'am, I am discussing about my case. Like if I am taking two alloys like 6061, two plate of 6061, having a dimension of 100 into 15 to 3 mm thickness,
Hmm.
and if we are joining it, so what I am doing is I am making groove, right? If I am making groove and I am adding some silicon carbide particle, like 13% silicon carbide particle. So this 13% volume fraction of the particle, so this 13% represent what? The total sample volume ka 13%, or only
No, no, no,
the
only the weld zone.
okay,
Because
means
in the weld zone, you are developing the metal matrix composite. I think.
okay. So I am using 13%, means 13% volume fraction, means if the volume 10 mm cube of my welded zone, so I am adding like a 2 mm cube volume, like this, like ma'am.
Yeah, kind of that.
Okay. Okay, ma'am, I understood your explanation. Actually, I had a doubt, like uh, means again the doubt remains the same here, like. If the particle size is bigger, it will attach the more grains, and particle size is a smaller, it will attach the
I
lesser grains.
understand your question, but it's totally
But
based on
but
the experimentation. You
yeah,
can say yes. I have found many literature where it is said that nanoparticles increase the ductility, but there are a lot of assumptions hidden over there which are not discussed. That what is the percentage of silicon carbide nanoparticles added there, and also in respect to what the particle number of particles were same in the comparison, or the volume fraction was same in the comparison, or the weight same, or the density same. What is the scenario?
Ma'am, actually, I was just reading some papers right now.
Okay.
So I had seen they have added like 3 percentage, three volume percentage, three different volume percentage of silicon carbide. One is 5%, another one is 13%, and next is 20%. So in conclusion, they concluded is. In case of 5%, if we are adding 5% volume fraction of silicon carbide, so the tensile strength will increase. And as soon as we are increasing the volume fraction, the tensile strength is going to decrease. Anyhow, the tensile strength after reinforcement will decrease from the base metal. So this is always true. But if we want to have some tensile property along with the hardness, so we have to go with the lesser volume fraction, like 5%. In 13%, it will decrease.
Yes.
Yeah.
Yes.
So actually, I was not. One thing I understood, like in case of alloy, that is different. In case of nanoparticle, is different. In case of alloy Mg2Si compound, it is already being formed because of the element present in it. So their case is different. In nanoparticle, we are adding from outside, and then there is a restriction. There is a pinning down effect between these, and in between somewhere there is a dynamic recrystallization because of some optimization of parameters. So there is a formation of some intermetallic compound we may get, like we are getting in alloy like Mg2Si, we may get after addition of SiC particle. So there may be a chances of some enhancement of ductility in or hardness both in case of uh, if there is a formation of Mg2Si. Because why we have ductility? Because of the percentage elongation. So because of the particle size. So if particle size is more, what I am understanding is कि if reinforcement particle is more, let us take example, my size is constant, like 20 nanometer I am adding. So 20 nanometer I am adding, like 20 nanometer particle size is constant. I am adding more particle, and in one I am adding less particle.
Hmm.
If I am adding more particle, tensile strength is getting reduced.
Hmm. Hmm.
But same in size, I am making size constant.
Hmm.
I am not varying the size. If I am adding lesser, so if I am adding particle means tensile strength is getting increased. So
I
I am
understand.
yeah, if I am adding lesser particle means the number of particle is less with constant size.
Hmm.
So tensile strength is getting increased. So this increment in tensile strength is because of what we can say the reason of it, because they have not given the reason, they have just performed the experiment,
Okay, okay, yeah,
and
I
they have
understand.
concluded it.
Okay, so I have not gone through any study material or book for this, so I also don't know this answer. But
Okay, ma'am.
it's a
Ma'am,
good question.
please, yeah,
I'll see and let you know through mail. You have
sure, ma'am.
mailed me once, na?
Yeah, yeah. Actually, we were discussing the same topic, and I thought to ask you because I have studied more than 8 papers. I will even send it to you in your mail also.
Yeah, you
Uh,
can send me.
yeah, and ma'am, please help me in this regard,
Yeah,
because
yeah, sure.
anyhow I have to give the reason. See
It's a
why
good
this is decreasing.
question and it's related to my research work as well. So definitely I'll see the answer of this question. It's a good question.
Sure, sure, ma'am.
It
Sure.
will
Thank you,
need
ma'am.
it
Thank you.
for my research as well.
Yeah, because ma'am, if we are telling like if number of particle is increasing means they have pinned down the dislocation, na? So if they have pinned down the dislocation means there is no elongation.
Hmm.
right now. Means what I was understanding, so there is no percentage elongation will become less
Yes.
if the number of particle is more, because they're just spinning down the dislocation. Even though they are attached with the laser grains, but they are more in number.
Yes.
I think, ma'am, you are understanding my question now.
Yes, yes, I understand.
Okay, okay. So, okay, ma'am, we will discuss. I think I have taken more time to you
No,
because
no, no problem.
I was a bit confused since morning.
Okay, okay, no problem. You just send me the papers. One second. I'll ask here. The
Sure,
I'll
sure,
ask
ma'am.
the professor.
Sure, sure. Thank you, ma'am.
Okay. Okay. So, Vanshika, do you have any doubt?
No, ma'am, nothing in particular, but it would be really helpful if we could
Yeah,
discuss.
I'll discuss all the topics. But before that,
Yes, ma'am.
whatever we have discussed right now, so
Ma'am, excuse me, ma'am. Can I interrupt, ma'am? Actually, I will not be able to attend the session because I am having some work in my lab now. So, ma'am, beforehand, I am giving thanks and extend my heartily thanks to you till now that you supported us, and especially in all the regards. So I am very thankful for this act of your lectures and all. And ma'am, yes, again, I will be on your mail, ma'am. And
okay.
if I get any doubt, so I will send my doubt to your
Yes,
mail, ma'am.
yes, no problem.
Right. But
Thank you so
but
much for
many thanks, ma'am, for this all the sessions that you have incorporated with us. And I
welcome.
think in the session, I think Vanshika and I think one Sanjit was there along with me. So we all really have got many more ideas from you,
Yeah,
especially
ma'am.
in my research also.
Really nice.
So yeah, thank you, Vanshika. Thank you for giving a cooperation at least with a teammate of mine in this complete whole week of this course. So thank you.
Thank you so much.
Yeah, thank you. Okay, ma'am. Thank you so much, Ananya, ma'am.
Okay. Oh, so Vanshika, you heard about the discussion that we were having, just right?
Yes, ma'am.
Do you want to comment on on this something?
No, ma'am, I was just trying to understand like what sir was saying and what you were saying. I don't have an opinion particularly on this,
So,
ma'am.
did you understand what I was discussing?
Yeah, ma'am, kind of.
Okay, okay, okay. So, if you got stuck anywhere or if you have any doubt, you just interrupt me and ask me. No
Sure,
problem.
ma'am.
Okay, so then let's start with the week 12 topics. So, the fatigue behavior in metal matrix composites were discussed. The comparison with unreinforced matrix we have seen for each of the cases. There was stress controlled, there was strain control phenomena, fatigue crack initiation and growth, how they are taking place in the metal matrix composite, which is different than the alloy, and the crack closure. Also, there was crack bridging, bending, trapping, etc. So, we'll see one by one those topics. First, first is the fatigue of MMC. So one thing to be remembered, as I said already, if you are adding some particles in the matrix, so if the particles are having their hands and legs, if this is the particles having hands and legs, so this particle will try to attach get attached with the matrix with as much force as it can exert on it, so it will try to restrict its growth. So if this is the matrix and if this is the particle, so if I am applying some load, this particle will grab the matrix and it will restrict the growth. So there will be some stress developed over the matrix wherever the particle is attached with the matrix. So it's like if this is a matrix, if there were some particles, so there will be some stress developed over the interface. Before, when we were talking about the alloys, if I was applying the load if in an alloy, there all the dislocation and grain boundaries belong to the aluminium metal only. So both all the things are similar. all the type of dislocations are similar. It can be either screw dislocation or edge dislocation. All the things are consist of aluminum atom only. The grains can be different oriented, but all the grains were having aluminum only. Some portion of Mg to Si or Si or Mg, that is very minimum. All the things are 99% is aluminum. But here the scenario is completely different. It's metal matrix composite, where you are trying to embed some particles over it. So there will be an interface in between the particle and the matrix. This is the interface. And whenever you apply some load, that load will cause some strain and stress over the body. If it's having some strain, then there will be no stress. If there is a lot of assignments that you have to complete, if you are doing the assignments, you'll not feel any stress. If you are not doing the assignments, if you are procrastinating it, then you will feel that stress. Similar way, if the materials is getting elongated, it will not uh, feel any stress. If it's not uh, able to elongate itself, then it will feel the stress. So that happens in case of metal matrix composite. The alloys can get elongated very easily. The stress strain curve of this is like this. So this portion, it's getting high elongation, strain. So in this portion, the stress is almost same. It's not feeling any stress. There will be some stress developed due to the strain, but it's not feeling any increase in the strain in this region. But the metal matrix composite is feeling that high stress due to the inability of to elongate, you can say. So why it cannot elongate? Because the particles which are embedded over the matrix is grabbing the matrix surface, and it's not letting the matrix to elongate. So this is why the interface and the stress intensity and the stress intensity factor at the interface is very critical in case of metal matrix composite. So whenever you are dealing with some metal matrix composite with different particle shape, size or amount, you cannot comment directly like yes, the hardness will always increase, but yes, the ductility will increase. No, the ductility will not increase. So it's very reverse phenomena. In case of alloy, when the strength increases, the ductility increases. There uh, we say that if the strength is if the strength is increased, means the ductility is increased, but if the hardness is increased, that brittlity is increased. But in metal matrix composite, you cannot comment on this. If you are adding some particle with lesser dimension, something can happen. If you are adding the same particle with more dimension, some different thing can happen. So this is why at the end of the week 12 lectures, it was said that you cannot anyway write like yes, this will be the expected property in the metal matrix composite, because it all depends upon the processing technique by which you are developing the metal matrix composite, and also the particles that you are adding and the size of the particle. So this is why the stress control or low cycle, high cycle, fatigue test, then nano indentation for hardness testing, these things are carried out. So here morely we are considering the fatigue of MMC by the fatigue testing. So there can be low cycle fatigue, can be high cycle fatigue. In case of alloys, there was work hardening. So I think you remember what is work hardening. So this is nothing but dynamic uh, what what was it called? Strain aging.
Yes, ma'am.
Dynamic strain aging means at the time of elongation, the hardness is increased. So that was known as work hardening. So in case of alloy also it was happening, and in case of MMCs also it will happen obviously. So in case of MMC, as I already said, we are not concerned about the elastic region phenomena. We are more concerned about the plastic region phenomena, because anyhow whenever you'll apply some load, if it's beyond certain limit, the particles will have the fracture, and there the ductility, hardness, everything will be different than the normal phenomena. In case of alloy, the graph looks like this for alloy, but in case of metal matrix composite, if you are having this composite with this much silicon carbide particles reinforced in the aluminum matrix, if with strain the stress is increased, because strain is not increased, then there is work hardening this region. Then the strain is again not increasing because stress is increasing, because there is fracture. So then after some point there will be some strain. So this region is extra in case of MMC. This is just an example that I am showing that it can happen. Ideally, our motive will be to not break the particles at the time of uh, any testing, because then the material will fail in the real application if the particles are breaking. But due to the breakage of the particles, the ductility may increase. So this is why the phenomena are a bit different. This is why we always deal with the plastic region of the metal matrix composite rather than the elastic region, because the elastic region is very less. So there can be work hardening, and due to the work hardening, already the cyclic ductility is very less in case of the metal matrix composite. Cyclic ductility means nothing like if you are going for some fatigue test. Fatigue test means you are applying some cyclic load, and if that in that cyclic load you are having some fracture or rupture in the matrix, then it means the the cyclic ductility is very less. In case of metal matrix composite, it's uh, very common, because whenever you'll apply more load than a certain amount, then the particles will get the fracture. So cyclic ductility is very low. But as you are going for cyclic loading, the hardness increases. So that is known as work hardening. So work hardening will give rise to more hardness. That means it can bear high load without getting fracture. So now after work hardening, we are going to the plastic region. Even if after work hardening we are getting some deformation, means we are having some plastic deformation cannot be regained, or the dimensions cannot be regained again. There we was knowing about the stress control and strain control phenomena. So for stress control means where the stress is low. Where the stress is low means it's the high cycle fatigue test, where the stress or the load applied load is low. But in case of strain control, where the strain is less. So strain is less means we are going for higher stress for very low time. We are not letting the matrix to elongate at that particular time. So at that particular time it will just fail after few cycles as the load is so high. So that is strain control. So in case of stress controlled, what happens is first the work hardening, due to which it shows higher um, fatigue life than the unreinforced material. So the graph was like this. This was for unreinforced, and this was for reinforced or MMC. As the this is the scenario for stress control. whatever load I am applying is lesser in this case. So this is an example of high cycle fatigue test, where the low applied load is low, so it will go up to lot more number of cycles. So here low load, so the number of cycles are more. This is the phenomena which is expected in case of metal matrix, because yes, we are going for the higher hardness material. Then if I am talking about the next scenario, which is the strain control, there the things will be reversed. As the applied stress will be very high, there will be sudden breakage in all the particles, even if it's small or big. If it's small, there will be detachment, and this is how the particles can get agglomerated in one state, and the matrix can get debonded with the particles, and wherever it is getting debonded, there will be some crack initiation, and if there is some crack initiated, then the crack will grow very fast due to that high stress. So in case of strain control, the scenario is completely opposite. In case of strain control or low fatigue cycle test, the it's often found that the fatigue life of reinforced metal matrix composites are lesser than the unreinforced. But before that, if I talk about the stress control, so whatever stress I have applied to the composite will be same that of whatever load stress I have applied to the metal. So if this is the total strain, then the total strain of the composite will be lesser than the total strain in the metal. And as a result, if strain is less, means it will take longer time to get more strength to fail. So this is how the fatigue life is more, and it's proved in case of MMC. So difference in the fatigue life is more pronounced at the lower stress level, because when you applied a lot of or when you have when the material have experienced a lot of cycles, in case of high cycle fatigue, at that stage it will more act like the unreinforced one. So the curve touches each other at the high cycle. If this is the cycle, this many cycle, up to this many cycle, there was a lot of difference in the reinforced and unreinforcement, but at that high number of cycle stage, the difference will be reduced, obviously, because there will be lot of strain generated in the composite as well, which strain is giving us the result of the failure. So it was calculated, there was some calculation for different R value, which is the stress ratio. I'm not going into that, but this is the scenario. But in case of strain control, so let's now talk about the strain control. In case of strain control, it's low cycle fatigue test. So number of cycles to failure is less, means the load applied is very high, so there will be no space for the percentage elongation, then the crack propagation, grain boundary detachment, those things will not take place. It will directly go up to the rupture point. So the graph will look like this. It will go to the rupture point. The strain will be very less compared to the stress. So this is why as the strain is less means you can control the strength. So in that way you can remember that this low cycle fatigue test is the strain control fatigue test. There the composite will act like this. It's the unreinforced, it is the reinforced. At the lower stage, both will act similarly, but again, there is a difference. So we'll not go for the low cycle fatigue, but again, it depends upon the application. If your application is something like your material has to bear this high stress, if your fatigue result that you are expecting for some application is low cycle fatigue, then you'll choose your material accordingly. Maybe you'll not go for the metal matrix composite, rather you'll go for some alloys. So this depends upon the application that for which you're opting or choosing the material. Then the total strain is equal to the elastic region and the plastic region summation. The total strain is always the summation of elastic strain and the plastic strain. Elastic strain can be restored by after the removal of the load, but plastic strain cannot be restored. But the total amount of strain that is happening inside the material will consist of both the type of strain. The elastic strain is much lower in case of composite, as I said, because of the embedded particles. It's attached to the matrix, and um, it's holding the matrix with its hands and legs, so it will restrict the matrix to elongate, and due to which it dominate the fatigue life, by which the fatigue life will lower down. So here, the fatigue life is less. Then the plastic strain life behavior. So the deformation is not uniform in case of metal matrix composite. It will always be localized. The deformation will always be localized. Can you tell me why it is localized, why it is not uniform? Any answer? No? Okay. So
Mom,
uniform.
is it because no, I'm not very sure, but is it because like the change in the cycle or something to do with that?
No, no. It's because if this is an alloy, then the alloy is made up of same grains. So there can be misorientation in the grain, but the grains are made of same particles. So whenever there is deformation according to the grain size and dislocations present over the grains will get elongated. But the elongation will be uniform to the lattice. But here in case of metal matrix composite, there are some grains, there are some particles, and there are some interface. So there are three types of things. In the interface, the grains will act differently. The grains where no particles are present will act differently, and the particles itself will act differently. When the load is applied, the load will directly go and affect the grain, the interface region. So obviously the interface will face more stress because there is a huge difference in the elasticity of the matrix and the particles. It's matrix, it's particle. So there is a huge difference in the elasticity, and due to which the in this time, due to the effect of load, the stress will be localized. So the deformation will also be localized. In this, if you understand deformation, dislocations by deformation, then in this portion the dislocations can move, but in this portion the dislocation cannot move. In this portion the dislocation can move. In this portion the dislocation can move, but in this portion the dislocation cannot move. So the deformation is localized, it's not uniform anymore. So this is why there is a loop and hysteresis loop in the stress strain curve, that however way the things are getting elongated will not get restore its shape and size following the same path. There will be hysteresis loop. So you understand up to this point that why there is a hysteresis loop in this, why the path of this elongation and path of this unloading is not same.
Yes, ma'am.
So it cannot be same in case of alloys as well. There will be difference, because obviously the same way dislocation has moved cannot come back following the same way. There will be some distortion, but in case of MMC the loop will be bigger. So up to this point was discussed till lecture 4. If you have any doubt, you can ask me. Otherwise, I will start from lecture 4. This was discussed up to lecture 3.
Yes, ma'am. This is clear.
Clear. Okay. Then from lecture 4, the crack growth and initiation and growth was discussed. So the mechanism of crack initiation, obviously the crack will initiate at the interface again, because that is the most critical zone. The crack may get initiated at the particles as well, because particles are brittle in nature. But if there is a crack in the matrix, matrix means where there is no interface, that may also happen due to the void, nucleation, and those things. So in all three cases, the crack growth will take place differently. If the crack is present on the matrix, if the crack is present on the interface, if the crack is present on the particle. So in the particle means it can lead to brittle fracture. If it's on interface, it depends, that it can lead to debonding, it can lead to some clustering, or some bending, or the crack closure can also take place, or the crack trapping or bridging can also take place if it's in matrix. There can be bridging, trapping, closure, or it can just simply propagate through the matrix if there is no particles sit over the movement of the crack or propagation of the crack. So if there are some sharp corners present over the particles which are embedded over the matrix, then they can act as the crack initiation point. Near that region of the sharp corner, the stress intensity can be more, and due to which, if there is a stress field generated over there, there will be pole of the stress, and that stress pole or the stress field or the stress intensity will lead to some crack initiation. Then if the particles are getting fractured, means if there is some crack in the particles may get fractured, and due to that the number of particles will increase, and as the number of particles are increasing, if the fractured particles are still bonded with the matrix, then now the number of interfaces have increased, and due to which the number of crack initiation site is increased. So there will be the effect of the crack initiation site, and there will be effect in the strength or ductility as well. Then in case of bigger sample, uh, the stress intensity factor will be more. This is the del K. If because the surface area which is exposed to the matrix, or the surface area which is embedded to the matrix is more, so obviously the stress intensity factor will be more. This is the stress which is getting generated or gathered over here, so those are more prone to fracture. Bigger particles are always prone to fracture, and if fracture happens, then the number of interfaces will increase. It will enhance the chances of crack initiation. So if we are saying like this was the size of the particle x, now this is the size of the particle which is y, 2y is equal to x. So number of particles are more, so crack initiation site is more. So I'll add bigger particles. No, the bigger particles will lead to fracture. But if you are adding smaller particles, then the surface area which is exposed to the matrix, which is embedded to the matrix, is lesser. So there the chances of getting the crack and the crack initiation site will be lesser than bigger particles. So this concept is reversed. So you'll understand more in the upcoming slides. So the crack growth will depend upon the stress that you are applying. Obviously, number one point. These are three zones in this diagram. It's a well-known diagram in the fatigue growth, or sorry, crack growth. One, region 2, and region 3. Three regions are having different phenomena. The second region is called as or known as Paris region, in which the crack growth is very minimum, but the stress intensity factor is increasing, so the stress developed there is much more. So that is a critical zone. So when it crosses a certain amount of intensity factor, it will just go up to the rupture point. It will have a very high and rapid crack propagation. But up to the threshold value, the crack will not, the stress intensity will not be that much. There will be a very minimum crack growth due to the stress that is getting developed inside it. But although this two graphs are looks like same, but it's not same. Here the crack growth is not that much, but here the crack growth is very high. Remember. So the Paris region equation is denoted with this. it's more like a power law again. So M is the work hardening exponent, and del K is the stress intensity factor, C is the proportional constant. So depending upon the M value, the things will be different, and depending upon the stress ratio as well, the things will be different. For different stress value or stress ratio R, for different stress ratio, the curve will be different. It's not like if you are increasing the R value, the curve will always go in the upward direction. It may happen that with increasing the R value, due to the different values of minimum and maximum stress, the curve may get lower down. Then with each cycle for different reinforced material, the curve was shown for this crack growth and stress intensity factor in comparison to the composite and the unreinforced material. So, so it's stiffer. So what do you mean by the steeper curve? Can you recall? Can you recall?
No one actually. I'm sorry, I haven't gone through the last half of the
Okay,
lectures.
okay, okay,
That
no
is
problem. No problem. Okay, so there can be three phenomena taking place. One is, I'm not writing it down here because it's long sentences. One is, if the del K threshold is increased, this is the del K threshold, pH. So if the del K pH is more, and the dependence of growth rate on del K in the mid range is also more. Some writing. So mid-range is the most crucial zone, because you see this threshold value will be dependent upon the exponent n and the stress ratio and the reinforcement. Most importantly, whatever particle you are adding and whatever size distribution you are adding, depending upon that, the threshold value will be decided. So don't consider, so we are not considering this 1 and 2 portion here. So we are only concerned about the Paris region, which is the second stage. So this is why it said like, if the del kth is more and if the dependence on the kth is more in Paris region, so it's like this can occur. So if you are mixing some specific amount of reinforcement particle in a specific matrix, and if your stress value is more, means your stress ratio is more, then three phenomena can occur. First one is this, second one is del kth is less and near threshold. The growth rate is more. And the third phenomena is lesser or equivalent mid-range growth. Its growth at mid-range means stage 2, and the del kth is also low. So all three things can occur at a specific stress ratio. So as I already said, na, you cannot comment like yes, if this is the stress ratio, if this is the number of particles added, this will work. No, this three thing cannot work. Other things you can also think of. So there cannot be any specific answer, but there are some explanation to each things can which can occur. So you have to distinguish those explanation, then only you can work with this type of metal matrix composite. It cannot be like there is no explanation, what anything can happen. No, it's not like that. But these three things can it mostly happens. So this is why these are being discussed here. So the graph can be like this. You see, this is the first case where the del kth is more. So this is the del kth, but this is the del kth. So the del kth is, this is for composite, this is for unreinforced. So the del kth is more in case of composite, but the mid-range growth is also more. So here the growth is less, but here the growth is more. Okay. The second thing is we are having some opposite things, means the del kth is less. This is the del kth for unreinforced and this is composite. So the composite is having lesser del kth, but at the same time near threshold the uh, uh, del A del N means growth rate is also more. This is the growth rate now. This is also having more value, means both the things are opposite and both the things can happen. Third uh, third scenario is where they can cross each other at a particular point. It can be like this. Up to certain limit the del kth was less. This is the composite, this is the unreinforced. So the del kth value for composite is less rather than the del kth value for unreinforced, but it's crossing the line at particular limit. So the great growth rate is more, or sorry, growth rate is lower or almost same. So this is the del A del N. So for composite it's lesser than the unreinforced. So all three things can take place. Again, it depends upon the stress ratio that you are applying. You cannot uh, control the stress ratio. So at the time of fatigue testing, you can control the stress ratio, but at the real application site, you cannot control the stress ratio. So depending upon the real application site, you are applying the stress ratio here. So you don't have control on that. But what on you have control, that is the percentage reinforcement, the particle size, and those interface bonding and those things. So this is why we are more concerned about the reinforcement rather than the crack propagation. The next thing is, but to model something, obviously depending upon these curves, we need to decide which amount of reinforcement and which size of reinforcement to add in the matrix, particle or fiber to add in the matrix. So this is why we are studying this topic, that what can occur. We are getting information about what can occur and then we'll go for the testing, so that at the time of testing if something happens we'll have the explanation of those, that yes, it can happen, so I am going in the right path. So lecture 5 consisted the different crack growth phenomena. This crack growth phenomena is typically for the matrix. So in the matrix, what can happen is, okay, in the matrix and the interface as well, not in the particle. So there we have talked about this three now. So now this two I'll be talking about. The crack on particle is simple. It can be brittle fracture. So one thing is crack tip phenomena. Crack tip, if it's sharp, then the chances of getting crack initiation is more. Next is crack closure. Third is crack bridging. By as the name suggested, all these things are very simple. You just try to get the things properly. Crack deflection, my handwriting is very bad, and crack trapping. So what can happen? One thing is crack closure. So the most important feature for crack closure is that the crack closure happens due to the roughness present over the matrix crack face. So this is because of the roughness. So if there is a crack, one is the, okay, tip I have already discussed. So I'm talking about the second one. So if this is the crack which is present over there, this is the surface, and if there is some surface roughness, as the crack propagates now, there can be thing like these 2 points will touch each other with time and with the propagation, and it will touch each other like this, and it will form a closure. So there will be two portion in the crack now, like this. There can be some void, or this void can again propagate and form a crack. So these things can happen, which is known as the crack closure. So crack closure is due to the roughness which is present over the crack. So it is also known as the roughness induced closure. So if there is a bulk material inside which there can be a lot of crack present due to the application of external load at the time of fatigue testing or any other type of testing, if there is a crack in the interface, if there is a crack in the matrix, whatever it is, this crack closure can happen depending upon the K value, which is the stress intensity. Then the third thing is this crack bridging. So first of all is crack bridging means two cracks are getting bridged. So it's like if there is one crack, if there is another crack. So I am drawing this in 2D, but you imagine it in 3D. If there is one crack and there is another crack which is in the upper plane. So if it's on plane 1 and if this is on plane 2, okay, these are micro level or nano level crack, and this, if this propagates, so one thing may happen due to the propagation, all the cracks are gathered at one position now, and all the cracks are getting bridged over one another. So the cracks are making some stack over there, some stack of cracks, and due to this stacking it will be called as bridging. So due to these things, two things can happen. One is the crack propagation will not be that much, but another thing can be like due to the bridging of the crack, now the crack opening is so much that it will directly go to the rupture point. So these are not some conclusions, but these are some scenarios that can happen inside the metal matrix composite when it is exposed to some externally applied load. The next phenomena is crack trapping. Crack trapping, one first one. assumption or one statement. Crack trapping is proportional to the matrix yield stress and the particle size root over. So as the particle size will decrease, the crack trapping will be more. So if there is a particle and this one crack is going there, so it can happen that this particle is so small that this crack cannot induce any other crack inside the particle. However, this crack will be trapped over there and the crack cannot move further to overcome this barrier of the particle. This is the crack, this is the particle. So just the way the dislocations were trapped in the alloys by the second phase precipitates, like that way the cracks can be trapped. And the next thing is that the matrix yield strength will also differ the crack trapping. Uh, Then also one thing, it's not like particle size. So okay, I'll decrease the particle size and uh, the crack trapping will also always increase. It's not like that. It's like up to certain point, the particle size will trap the crack. But if now the particles are having 1 nanometer, 2 nanometer diameter, if it's spherical, then it cannot trap the crack. Na? The crack will overcome the barrier of the particle and it will just propagate. So there is this few things. Next one was crack deflection. Okay, crack trapping was the fifth one. The fourth one is crack deflection. So it's like if there is one crack and this tip is not sharp enough, then this is the particle present over there, so the crack will be just deflected over there. The same things which were happening in the case of dislocations, the same things can take place in the case of cracks as well. So because we are talking about some micro level cracks here, not the bigger cracks. So yes, this is the deflection. It will just deflect, it will just bend there and to propagate. So these are the things regarding the crack propagation. Other than that, as I already said, you cannot comment directly on the phenomena which are taking place there due to the change in the particle size and amount, but you can just expect that these are the things, this is the list of the things that can happen. So similarly, if you're discussing about the mid-range growth, that is for stage 2, the stage 2 growth, there the cyclic loading can lead to work hardening. So there can be the dynamic fracture, that at the time of loading the fracture is taking place, or there can be static mode of fracture where the particle are fractured and you'll get a sudden fracture in the whole material, or it can be like matrix void nucleation, then void growth, then coalescence of the void and it's getting filled. So both the things can take place. Then the next topic is effect of microstructure. So as I said, the particle volume fraction if increases, the fatigue life will also increase. But again, the volume fraction also depends upon the particle size, because if the particles are more, the fracture life, you cannot say like the fracture life will increase, but if the particle size is more, the hardness will be very high, the tensile strength will be very less. But if the particle size is lesser, the hardness will be more, but the tensile strength may get increased. And near threshold also means the threshold portion is also very critical. Threshold portion means this portion. This is the this is the threshold portion. So near threshold portion, small particles may behave differently, smaller particles may act differently, bigger particles may act differently. So you'll have some references. If you, when you'll be going through the lectures, you'll see, you'll have some references. By seeing the reference, by gathering knowledge from the reference about certain, about the aluminum alloy that you are going to work with, you'll decide how much amount of reinforcement particles to add and which size of the reinforcement particle to add. So this was discussed up to the fifth lecture of week 12. If you have any specific doubt, you can ask.
No, ma'am. I'll go through the last part myself once, ma'am. I got some idea. I didn't watch the lecture for the last
Yes,
and the
yes,
second
you'll get
last.
some idea. After that also, if you have any doubt, or whoever will be watching this video, if have any type of doubt, my email ID is always there. You can drop a mail. Other way, you can drop a message on my LinkedIn as well. I'll try to get back with the answer. So
Sure,
another
ma'am.
thing is the aging. So you are talking about, we are talking about the metal matrix composite, where we are adding some reinforcement particle, and depending upon the particle size, distribution, these things will get different metallurgical property, mechanical and metallurgical property. At the same time, we are dealing with the aluminum alloy also. So there can be aging, underaging or overaging in the aluminum alloy. So the, as Sailesh also asking, over the effect of the aging, the reinforcement will also affect, the reinforcement will also change the mechanical and metallurgical property. So you'll also have to see the aging condition of the aluminum matrix along with the reinforcement condition. So this is all. So I have few questions from the last year assignment for week 12, so that you can get an idea about what are the questions and how to attempt the question for uh, this year 12 week question. So the first question is, for a completely reverse stress cycle, the stress ratio R value will be, yes, the R value,
Ma'am, -1.
yes. Then amplitude ratio in terms of stress ratio can be written as,
Ma'am, I guess 1 plus R by 1 minus R.
it's 1 minus R2 is 1 plus R.
Oh, okay,
It's
okay.
a minimum by maximum. At a given maximum stress value, and when the stress ratio is not equal to -1, which of the following stress ratio can have highest fatigue limit?
Ma'am, is it plus point 0.3? I'm not very sure.
It will be, if it's point plus point 0.3, it can be plus point 0.4 as well, now, because point 0.4 value is more.
Oh, yeah, in the lecture it was discussed, yes.
So it's more means it, the fatigue limit value will be more, but up to certain point, obviously. In the SN cards, which of the following materials show well-defined fatigue limit?
Steel and titanium.
It's titanium mostly.
Ma'am, but
That
steel also has a fixed value.
steel also show a very well-defined fatigue limit, but maybe in terms of comparison, they have set the answer
Okay.
like titanium, but it's having more defined fatigue limit. Then, which of the following statements is or are incorrect about fatigue crack initiation and propagation? One is, generally fatigue crack initiate at the material surface. In the material subjected to fatigue load, slip lines are observed in some grains and other are free of such slip line. Present persistent slip band are embryos for fatigue crack. Fatigue cracks are purely intergranular in nature.
Ma'am, I guess fourth one is incorrect.
Yes, so fourth one is incorrect, but the rest that generally yes, fatigue crack initiate at the metal surface. Metal subject to fatigue load, slip lines are observed in some grains. Obviously, or throughout the things will not be present in alloys. Even it's not throughout the grains, and this composite is even will have localized deformation. So obviously slip lines will be observed in some of the grains, other will be less free of such slip lines, and the persistent slip band will act as an embryo for the fatigue crack. Which of the following statement is are correct about the fatigue of MMC?
I guess all are correct.
Um, it's the fourth one is not correct because constraint deformation to the matrix with respect to the reinforcement leads to development of anaxial state of stress and steep stress gradient in the matrix
Oh,
around reinforcement particle. So
it's triaxial, is it?
uh, yeah, it's not correct now.
Yeah, ma'am. Okay, it should be triaxial state of stress.
And also the okay, no problem. It will be triaxial anyway. There is other thing also, another thing. Uh, no, it's okay. I forgot. Statement 1. Stress control fatigue is low cycle fatigue at lower stresses. Strain controlled fatigue is high cycle fatigue at higher stresses. Which is correct, which is wrong?
I guess first is wrong, and so it's the second is train control fatigue.
First of all, if first is wrong, then the second will be also wrong, na? Because there
Yeah,
is only two types of things: stress control and strain control.
yeah.
And also over that, low cycle means lower stresses. No, low cycle means higher stresses.
Higher stresses and less cycle.
This thing is also false. And also low cycle higher stresses means strain control.
Yes.
So both the statements are false. When we compare the aluminum copper alloy with its composites under the condition of total strain control fatigue, plastic strain in the composite is, I have already discussed the topic.
Higher than the plastic strain of the alloy.
So that means the fatigue life is decreased in case of composites because the strain is more here. So it will have lower time to get failed than alloy. The next question is select the correct statement below. Yeah, it's almost same question. It's kind of explanation of the question 8. Don't mug up the things. You just try to explain
Ma'am,
later.
ma'am, is it the fourth one? Like, it should.
No, it's the explanation of the last one, na? You
Ma'am,
mentioned
but I,
higher plastic. You have answered that it will
yeah,
have
ma'am.
higher plastic strain. Means it will
Yes,
have lower time to get fed.
yeah,
Means the fatigue life is less.
less.
So here, if strength control fatigue resistance of composite is inferior, lower than the alloy.
Yeah, ma'am, that's right.
है ना?
Yeah.
Yes. So in the stress control condition, the fatigue life of MNCs get dash by dash the particle volume fraction. You tell me first one.
Ma'am, I feel like it should increase. Like, I'm not getting this, ma'am, actually. I think it should increase by increasing the volume fraction of the particle.
Yes. So where you were feeling the doubt?
Ma'am, because like what you explained in the class, if I keep like in one side, ma'am, and I think that like increasing the volume fraction, if I am going to like it's supposed to decrease the crack and propagation, ma'am. Like you're adding something extra to a thing, so I find it a bit counterintuitive. That's why.
You tell me again. You repeat the question. When you are increasing the volume.
Like if I'm adding in a composite, like I'm adding some reinforcement, so it's like another particle that I'm adding.
Yes.
So like it should decrease the stress at which the this material will show fatigue. No, like
This is why your fatigue life is increased.
uh, mom, stress is decreased. So like how is like fatigue life?
So stress is decreased. Okay, no, not stress is decreased. One. Let me find out quickly. So when you are applying some load at the interface, you are having some localized stress, and that is getting increased. The stress is getting increased. Okay. When you are increasing the volume fraction means more number of particles are added, and now the stress is getting more increased, but the strain is getting reduced as the volume of the particle is increased. So strain is reduced means it's not having that much strain. So in the plastic region also you are not having that much strain. In the plastic region also it's having a steeper curve where the strain is less compared to the stress it is having. So होने दो इसको stress feel, no problem. As soon as we are not having the brittle, we are not entering into the brittle zone. If the composite is behaving like ductile, up to that limit we can sustain that strain. We just want
Oh,
that
okay, mom,
the
got it.
strain will start after some more time than
Yeah,
the
mom.
alloy,
Yeah, mom.
because the
Mom,
elastic
actually,
strain will always be lesser in case of composite.
yes,
Elastic
mom.
strain cannot be that much, but we can control the plastic strain. So we are doing
Ha,
so. We are controlling the plastic strain. We are trying to reduce the plastic strain so that we'll have more fatigue life. We'll have more time to fail. The failure will be after
yes,
more
mom.
time. Okay,
Yes, mom.
now you understand. But
Yeah,
at the
mom.
same time, it depends upon the dimension of the particles as well. It's not like if you are adding microparticles or you are adding nanoparticles, always the the hardness will increase or the stress will increase, so the strength will increase. It's not like that. As I said, the nanoparticles can get can sustain that elongation because it cannot grab the material that strongly. So it will just elongate, it will get elongated, or it will not get debonded, but it will flow with the material. Before, the particles were grabbing the material, the matrix, like this. But when the particle is this much, it cannot grab the matrix like that. So it will just flow with the matrix. The bonding will be as it is, but as the dislocation will flow inside the matrix, the particles will also flow in the matrix. So this is why the particles are adding some hardness, but the particles are unable to add that tensile strength. It is adding some ductility in the matrix. But the bigger particles are adding lesser tensile strength in the matrix. So up to this point, you understand?
Yes, ma'am.
Do you have any other doubt, or it's okay?
Ma'am, actually, I'll come back to you if required by mail because I didn't go through this week's lectures too well because it's.
Okay, okay, no problem. Um,
Thank you so much,
at
ma'am.
any time you can mail me, you can ask your doubt regarding this class. So this is up to week 12, and this is all about the 12 weeks doubt clearing session for NOC MM40 aluminum based alloys and metal matrix composite. So thank you so much, everyone who have attended the live session, who have seen the recording, whoever has asked the all the doubts, whoever have mailed me for the doubts. I am overwhelmed. Thank you so much for attending and for supporting me in this TA shift. Thank you, and hereby I am ending this session.
Thank you so much, ma'am.
Also, Navratri has started, so Shubh Navratri, Shubh Durga Puja as well.
Thank you, ma'am.
Yeah.
Thank you very much, ma'am.
Bye. Bye. Good night.
Good night.